Log on, tune in, find out. Another good idea from Cambridge.
So first of all, I would like to thank the organizers both of this conference for giving me opportunity to speak. Also, I'm afraid that I'm a bit on the boundary of discrete harmonic analysis. And also for this wonderful thematic program I spent here. Very nice 2 months, so thank you for invitation and possibility to be here. Okay, so this is based on joint work with Rademacher, who is also here. But I will try to get you also some review of known results, not only for Rademacher chaos, but also for Gaussian chaos, which is related somehow. So we will go in half an hour probably to the latest results. But first I will review some known approaches. And okay, I at the moment notation may be a bit tough, but I hope, please interrupt me if you don't see something. Okay, so our main object of study is so-called random chaos of order D. So what is this? This is just a polynomial or multilinear form in independent random variables. So we assume that xi's are independent, and I will be talking about special types of polynomials. So they are called so-called homogeneous and tetrahedral. Homogeneity is clear, yes, but there are terms only of the same homogeneity, so homogeneity D. And tetrahedral means that there are no quadratic terms of terms of higher order. So we exclude terms like xi squared or xi third, etc. So this will be for let's say for order 2 is just a polynomial of degree 2 without squares and linear terms.
What's undecoupled?
Okay, what's undecoupled, it will be clear in 5 minutes. It basically means that variables, second variable and first variable, there are some dependence on the variables in the second position and first. Okay, in a few minutes I will show you what decoupled means, and I think it will be clear. So 2 important cases. So one is the subject of my talk is Bernoulli or Rademacher chaos, which is when we take xi to be independent, symmetric, plus minus 1 random variables. So it depends if you are probabilist or analyst, you call them Bernoulli or Rademacher. And another important example is obviously Gaussian case, which should be the simplest. If you are able to prove something, you should be able to prove it first for Gaussian by the central limit theorem, and then try to extend it to other random variables. At the end, maybe I will be talking a few words about other random variables, but I will concentrate on these two cases, and I will be looking for two-sided estimates for moments or tails of S. So estimates that works both from above and from below. Okay, so this is notation, a bit of notation. It's typical, so I will not say a lot of it. XP, it means LP norm, so normalized moments, that is expected value of x to the p into 1p power. We write f is equivalent to g, so if they are of the same order, it means that they are comparable with a constant, either with a constant universal constant or a constant depending on dimension. If it depends on the order of some parameter, we write this parameter of dependence here. Okay, and trivial observation is that this product is invariant under permutation. So it doesn't matter if we write xi xj or xj xi. So we may write this is the same as 1/2 sum over I not equal to j aij xi xj, yes, or in general 1 over d factorial. And it's often easier to work with whole matrix and assume symmetry. So what I would mean by symmetry assumption, I would mean that the matrix is symmetric under taking permutation, and also because it corresponds to this tetrahedral Hodges without squares. So I will assume that if two of the indices are equal, then the term in the matrix is 0. This way we will have the whole matrix, not only the matrix under diagonal. Okay, so there is a relation between moments and tails. This relation goes both ways if you don't care about the constant. So here, all results I will present will involve some constants. There are situations that we would like these constants to be 1, but this is quite a different topic. So one relation is obvious. Every student knows it. That if you have a moment, then by Chebyshev Markov inequality, probability that z is bigger than e times LP norm is e to the negative p. So this holds in general. And one may reverse this inequality. This is due to so-called Paley-Zygmunt inequality. What is Paley-Zygmunt? Paley-Zygmunt is that if we have, let's say, variable z, okay, maybe not z, y bigger than 0, then Paley-Zygmunt is that probability y is bigger than 1 minus lambda e of y. Okay, lambda e of y is bigger or equal than 1 minus lambda square e of y times e of y square. Okay. So this is Paley-Zygmunt inequality, and if you apply this to the piece power of z, and you need some comparison of second and first moment of this piece power, that is comparison of two piece moment and piece moment of z. So if you have this comparison, you may reverse this inequality. Again, losing a bit at the constant, obviously, but it works very well, as you see. And okay, this assumption is not very restrictive. For all cases I will discuss, we have this comparison between piece and two-piece moment. So for Gaussian or Rademacher, we may, for example, use hypercontractivity. I will discuss in a minute, and they are comparable with some constant exponential in D. So here this will depend only on D if this is this chaos. And what does it mean? It means that if you are looking at the piece moment, it is more or less the same if we are looking at the quantile of random variable of the order e to the negative p. So here again, we lose at the constant, but up to this constant it is the same. Okay, so
I wasn't managing. I was too fast. The last line on the slide. What does it say again? That the pith norm is.
The pith norm is basically the point when random variable probability that the tail that modulus of s is bigger or equal to t attains e to the negative p. So it's infimum because this may be discrete. It has some atoms, yes. So but basically you look at the point where probability of s is the tail is e to the negative p, and okay, if s has continuous distribution, it's well defined. If it has atom, obviously it's not, and basically this tp or what was notation qp, this qp is the same as p norm. Okay, so first result, I think I should mention here more names than just Bonami and Beckner, probably also Gross and Nelson. So some of those people like Bonami proved it for Rademacher or for Fourier on discrete group, some like Gross for Gaussian. But anyway, what does it say, this hypercontractive inequality? It says that moments, if you deviate from 1, I think that the last talk of this conference will be what happens below 1. But if we deviate from 1, then the moments are comparable, and the constants depends polynomially in D, and it's more or less optimal. So if we plug, for example, q equal 2 to have just square root of variance, it doesn't matter if Gaussian or Rademacher because they are of variance 1. So it means that P's moment grows like P to the d half if we don't have any assumption on the coefficient times square root of variance. And square root of variance is just sum of coefficients squared into the power 1/2. Okay. Okay, in terms of tails, it means this, but if you are looking at probability S is bigger than T, this function is, one may easily reverse this function, so this is why we have this T by variance of S to the power 2 over T. So, and this works both for Rademacher and for Gaussian chaoses. This is uniform band, the simplest possible, and basically it's optimal. If we know only the variance of a chaos, we cannot do better, because if all terms are very small, if the matrix is, let's say, of rank 1 in two cases, whatever rank means in multidimensional case, then this is optimal. For example, products of independent Gaussians behave like this. So this is the right tail. So, however, in general, it is far from being optimal. So you will see in a moment for Gaussian that this behavior, so even for d equal to 2, is exponential behavior. And in some situation, you may expect Gaussian behavior. So this inequality doesn't show it. And also, it doesn't take into consideration the fact that Rademachers are bonded. So this is the other obstacle here. But in general, it's very nice inequality and very useful. Okay, so now easy observation, but maybe some of you miss it somehow. So that Gaussian chaoses dominates Rademacher chaoses with just again exponential constant, and this is trivial use of Jensen's inequality. So you see, if here we assume that Rademachers are independent of Gaussian. So Gaussians are symmetric, so we may represent them as Rademachers some Gaussian. So we may, so this is by Fubini, this is double expectation, one with respect to EI, one with GI. So we may put one of expectation inside because x to the p is a convex function. So it means that we keep outside the expectation with respect to Rademachers and inside with Gaussian. And the first moment of Gaussian is just, I guess, probably I was cheating here. It's square root of p by 2, not 2 by p. But okay, so it should be like d2 by 2. But it doesn't matter. It's a constant, so it's a constant to some power times Rademacher. So you see that if you have an upper bound for Gaussian, it will work as well for Rademacher. With the lower, it's not true. Okay, so this is this, and also, okay, sometimes so Rademachers has one drawback, that they are discrete, so they have atoms, and sometimes maybe it's better to work with variables without atoms. So you may as well take uniformly distributed random variables on interval -1, 1, say, or -1 square root of 2, 1 square root of 2, I guess, if you want variance 1. Okay, and then up to order. So again, exponential constant, there will be these two things are comparable. So sometimes, for example, these things has nicer concentration properties. Also, you may work with both. Okay, so now I will go to Gaussian case, but let's first look at the simplest possible situation, sums of independent random variables. So Gaussian or Rademacher. So for Gaussian, there is nothing to say. The Gaussian, obviously, sum of Gaussian is Gaussian. So it's just your parameter is just the variance is sum of AI square. So it means that we have this equation, and then the only thing here to observe is that P's moment of Gaussians grows like square root of P. So if you want precise growth, it's, I guess, square root of P by E. by square root of e, but you know, here we don't care about the constant. Okay, so what about Rademacher's? Let's immediately compare it to Rademacher's. So the previous slide shows that this should be upper bound for Rademacher. But obviously Rademachers are bonded, so we should take into consideration the bondedness of these. So they are bonded obviously by sum of moduli of coefficients. So if you take these two things, but one that they are dominated by Gaussian and other that they are bounded, you easily derive upper here bonds, but they are smaller than sum of, let's say, p largest coefficient, and then Gaussian bound on the other term. So upper bound here is trivial, and it works not necessary for p. So here we may take, if you want, upper bound anything. Yes, it's obvious. What is not so obvious here is the lower bound. But if we want to estimate it from below, we should just take p's largest, treat them in separate way, and then the other coefficients, it is Gaussian. Okay, so equivalently in terms of terms of tails is the following: that if you are looking at the this quantile e to the negative t, you should take here p equal to t. So you sum t largest coefficients and then square root of t times L2 norm, so of the other. So, and the other way around. So obviously people who work with interpolation notice that this is some interpolation norm between L1 and L2. And okay, so basically Montgomery Smith, he was looking for tails. Hitchenko translated into moments. Nice. Okay, so let's now review results for higher order causes for the Gaussian case. So in 71 there was a paper in some, I think, Annals of Statistics or some statistical journal, and it was not noticed by some other people. So this result was reproven by several other people, including Talagrand later on. Okay, but it was proven in 71. But what happens for Gaussian causes of order 2? So again, we assume this symmetry assumption, so there is no diagonal, and Aij is Aj. So there is a thing. So this is the growth. So this is variance, or it means Frobenius norm or Hilbert-Schmidt norm of metrics times square root of p. So this is Gaussian behavior. But I told you that if you have a product of Gaussian, it grows not in the Gaussian way, but in the exponential way. So there should be p times some other parameter, which is usually much smaller.
I don't understand this notation. What are the index beside the norm? You have a
1,
2, and
okay, it will be clear if I generalize it into higher order. So for you, I want to introduce this notation at this moment because it will agree with my further notation. But at the moment you may think of this as Frobenius or Hilbert-Schmidt norm. And that this, okay, so this 1, 2 means that you take supremum over variables in x in first variable.
You're looking at it as an operator from L2 to L1?
No, okay, so I may explain you as this. This notation means that you treat these two variables as one variable. So it means you take supremum, you treat it as linear form on L2. So you take this over L2. Okay, for order 2 causes there is little sense of introducing this notation because it's obviously square root of some Aj I square, but for...
What does it mean when you have a 1 and a 2 on the first line in the first formula there?
Define in the middle, define them. Don't
There's, what does it mean when 1 appears in a 1 curly bracket and then 2 appears in a different curly bracket?
Okay, so for, there are two ways of splitting of splitting the sets of 1, 2 into disjoint sets. One way is this, and the other way is this.
Okay.
And this corresponds to this thing, and the other corresponds to this. For higher order, there will be more ways, and then the things will get more complicated.
Okay, but
so
so it corresponds to this, and what is this? Can you just? I'm trying to slow you down because I can't follow the notation, so I don't understand.
okay, so obviously you may treat a matrix as a two linear form,
Right.
but also you may treat a matrix as a just linear form.
Right.
Yeah. So one is a norm treating as a matrix as a linear form on L2, and another is treating a matrix as two linear form. On okay, so this is this, but you know, for a moment you should think about Frobenius and operator. Okay, so this, you know, this function is very easy to find the inverse. This is why you have such nice formula for the tails, and this is exactly what Hanson-Wright proven was upper estimate of the tails. Also, I think they realized that it is close to be optimal, and I think it's not in their paper, but they knew that it's almost like this. So they showed examples that you know you cannot improve, also not in the whole generality. Okay, so what does it mean? That the tail, okay, up to some point is Gaussian, so close to for T small, because this quantity is usually much bigger than this. Operator norm is much smaller usually than Frobenius norm. Oh, at least in the cases if A is high rank matrix. If it's rank 1, they coincide. So close to 0, you have Gaussian tail. Far away from 0, you have exponential tail. So it's exactly like in Bernstein inequality. If you have sum of independent bounded random variables, close to 0 they have Gaussian behavior, farther away to 0 they have exponential behavior. Okay, actually they have a little bit stronger, but here it's just Bernstein type estimate. And what is nice that it works two sides. And okay, I will give you a proof. The proof is just several lines, and it's basically the proof where you find what you may find in Hanson-Wright paper. So basically, all the people I think follow this way. Okay, so what is nice about symmetric matrices? Because we assume this symmetry. What is nice is that they may be diagonalized in orthonormal basis. Yes, everyone knows it is linear algebra, but there is diagonal matrix with some entries such that A is C inverse D, well C is orthogonal matrix. But what is crucial about the Gaussian distribution, canonical Gaussian distribution in Rn, that it is rotation invariance. If you rotate it by any matrix C, it will again be Gaussian with the same covariance matrix. So it means that it doesn't matter if you look at the matrix A or a matrix D. They will give the distribution of this thing, and this thing is the same. Okay, so it means that also the norms are the same. But what is the gain here? The gain here that these variables are independent. GI square are independent, here they were dependent. Okay, now the trace agrees because this is C inverse, and you know, by now nice properties of T. So trace of D is the same as trace of A, but we assume that there is 0 on the diagonal. So we may as well assume that sum of AII is 0. It will work also in this situation. So we may subtract 1, and sum of DI is sum of AII, it's 0. And now it's a standard thing that instead of maybe looking at this, we may symmetrize. Instead of taking out, subtracting expected value, we may multiply it by independent Rademachers, maybe losing a constant 1/2 or something. Okay, so here it's up to 1/2 is this. And what is nice about these random variables, they are independent, symmetric. It's easy to compute their tails. So what did Hanson and Wright? I think they computed Laplace transform to get to like in Bernstein inequality. You compute Laplace transform, and then you find that it's finite up to lambda smaller than 1 over maximum di, and you inverse it and you get this estimate. So this is upper estimate. To get lower estimate, you should work a bit harder. It was a trick found by Guskin and Kvapin to show that the Dumer reverses. But here it's not very hard to show both upper and lower bounds. Okay, so now we should look what is maximum di. But what is maximum di? Maximum di is operator norm of D, and operator norm of D is the same as operator norm of A. So this is AL2 L2. And now what is Frobenius? What is sum of di square? Is Hilbert-Schmidt or Frobenius norm of D, and it's again the same as, because it's sum of squares of the eigenvalues. So it's Hilbert-Schmidt. Okay, so you see it's few lines proof. If you want details, I didn't give you details of this, but it may be written on 1 page or 1 page and a half. Okay, so but if you want to generalize it to higher dimensions, we get into trouble, because for matrices of order 2, there is this diagonalization theorem. I don't know such theorem for matrices of order 3. I asked some algebraists, and either I got no answer or I got an answer I didn't understand. So I don't know. As far as I know, there is nothing as simple as here. So you need another approach to causes of order 3. You cannot just use this diagonalization. Okay, and another approach is based on so-called decoupling. So now I will answer your question: what is decoupled and undecoupled? What does it mean? Okay, so at the beginning we assume that xi are independent. Now take a copy of each sequence. So take the independence copy of the sequence and transform this chaos when you have xid into chaos when you put in each place independent random, random variable from independent sequence. So instead of looking at this, okay, you look at the chaos decoupled. Okay, so for order 2 it's sum aj xi1 xj2. And for higher order it will be more terms. So what is the theorem, and what is why it is so nice? Okay, so the theorem is that if you have these symmetry assumptions at the beginning, then the decoupled chaos and undecoupled chaos have the same tails. Unfortunately, there is a constant here that depends on the order. And this constant is terrible. Even for d equal to 2 is not so nice, and the growth is this. It's really large. So maybe somebody may work on this constant. But if you agree to lose on the constant, this is very nice, because instead of looking at undecoupled chaoses, you may look at the decoupled. Okay, so what is the gain? Okay, here again a polynomial, here a polynomial. Okay, why should one bother? Why this is nicer than this? Because you may use induction, yes? You may, for example, fix first d-1 variables, then treat it as linear form into last variable, use bounds for linear forms, get something that depends on the first d-1 sequences, and etc., etc. So this is general policy how to do it, but use induction on D. Due to this result, without decoupling, induction is much harder, because you cannot fix like xj and say that first variables are independent, because they are dependent. Okay, so now I told you that we cannot use the same approach as Hanson Wright. So first result, I think, was shown in Bohler. It was published in some conference proceeding. It was not as nicely written, I think, and so Arkones and Zinev found, I think, a bit different proof of this. and also with nicer notation, I guess. So what did they show? Okay, for order 2, remember, it was square root of p times some Frobenius norm, Hilbert-Schmidt norm, plus p times operator norm. So it was polynomial in square root of p of order of degree 2. Here is again a polynomial of square root of p, but of degree d. So there are d terms here. So square root of p times something plus p times something plus p2, 3/2 times something, etc. And you have this thing. So this is a nice formula if you want the theoretic result. It's it shows that the growth is polynomial. So if you look at the growth in terms of p, it's very nice. But if you want to compute the thing, so estimate, it starts to be messy because it's supremum of some Gaussian process, or even this is again a polynomial. Notice that if k is smaller than d minus 1 or d minus 2, it's polynomial. So it's even not Gaussian. It's in a couple of Gaussian variables, and you have to compute this empirical norm, which is not as nice. Only the thing very easy to compute is for k equal to 1, I guess, because then it turns out that this is just a variance by very easy computation. So this will be square root of p times square root of variance plus some other terms which are not so easy to compute. Okay, so now this notation. So you see now. Okay, I will have next slide for d equal to 3, but it will be easier to digest. But in general, what do? You split your set 1 over d into k disjoint sets, and you treat this A as a multilinear form, but not d-linear, but k-linear. So you indices in one set you treat as one index, in fact. So you look at this D multi-index matrix as in fact k-linear form on L2. So it's a tensor-like norm, okay? And what do you do then? You have again a polynomial p over. So the coefficients are the same as Arcon-Regine, and you take all partitions into k sets and you compute this quantity. Okay. So maybe it will be easier to look for d equal to 3. So for d equal to 3, basically there are 3 types of partition. Either trivial partition into one set, so you treat as linear form, and this is exactly variance by the duality. Then you may make partition into 2 sets. It means that you treat indices j and k as one index. So you look at this as a 2 linear form on L2 times L2. And okay, you may use duality to have a slightly simpler formulas also, still they are not as simple as here because still you cannot reduce it nicely to something without suprema. And also the last partition is the partition into 3 sets, and now it's 3 linear form matrix of order 3, and you have this. Okay, so it's basically as for order 2, yes. If this is why I introduced this strange notation 1, 2, 1. This curly brackets before, because I was motivated by this. But this is the same. Okay, and this polynomial look like for partitions in one set, you multiply by square root of p. So this is square root of p times square root of variance plus p times, in general, if you don't assume symmetry, there are 3 terms. If you have symmetry assumptions, all these terms are equal. And then there is this 3 linear form. Okay.
Are the indices correct? No.
Oh yeah, I made usual cut and paste procedure, and I read these slides at least 4 times. But okay. Today in the morning, I made 2 corrections, but still, there are infinitely many probably mistakes. Okay, so the theorem, in this compact formation is nice to formulate. But I formulated in the decoupled case, but in the undecoupled case under the symmetry assumption, this is the same. So it's a bit more general because here you don't assume symmetry. For the decoupled case, for the undecoupled case, you need to assume symmetry. And you have this, or in terms of tails, because maybe it will be easier to digest for tails. Okay. All right. So there are Gaussian tail near 0, so t squared. Then there is t term at some interval. Then there is t to the 2 third term, etc., up to t to the 2d. Unfortunately, all these terms may appear. So there are examples that the case terms dominate. So this is a bit unfortunate thing. So maybe let's look how it looks for order 3 and undecoupled. So the thing of our interest. So for order 3, moment square root of p times square root of variance, p times these 2 linear norms plus p to the 3/2 times this 3 linear form. Okay. And the tail, Gaussian, then exponential, then t to the 2 thirds. So like Gaussian into 3/2. Then Gaussian third, exponential into 3/2. Okay, and then the upper agree with lower, up to a constant. So here, the constants here are a bit terrible because of this decoupling. So this is the really thing that makes them not so nice. Okay, so there are how to get this result. So for lower estimates are trivial. This is basically induction. Okay, if I have time, I will show you this for Rademacher. But the only thing to notice here that expected value of supremum of process is bigger than supremum of expected value. Basically, this is it for lower estimates. And one trick. Upper estimates, okay, you use induction, use Gaussian concentration, then this reduces to the result of Arconnes-Ginet, and you are stuck with this empirical expectation of empirical processes, and you have to do something with it. Okay, so here is the inequality that is necessary. So you have a Gaussian matrix, so non-IID. This is a bit of complicated correlation structure, and you need to compute operator norm or L2 tensor norm of this thing. So let's look how it looks for d equal to 3. So for d equal to 3, it reduces to the following thing. So you have Gaussian matrix, but with non-trivial correlation structure. So here the entries have different variance, there might be correlated, so it's not that trivial. And you want to find the upper bound on this. So one thing that must appear, you may how to estimate norm of a matrix. You may take maximum of norms of rows and maximum of norms of columns. This corresponds to these two terms. And then, then there should be something else, and it turns out that this something else is, estimate by Frobenius norm is trivial, so, but it turns out that you may gain something. You may divide this trivial estimate by square root of p, but multiply by square root of p times this 3 linear term. Okay, so it's not that easy result. It is based on chaining techniques and estimation of some entropy numbers. So it's not enough to use Dudley results for specialists here. You should use something like majorizing measure theorem. Okay, so there is a related problem I would like to pose. I was working hard on this problem without much success. Okay, so the problem is the following. It's very easily formulated. You have a Gaussian random matrix, but you don't assume as in standard matrix theory that they are IID. If they are IID, everything is well understood, even there are terrific results. But for non-IID case, there is still a problem. What is this expected value operator norm? Okay, so trivial estimate from the bottom will be to take maximum norm of columns and maximum norm of rows. And the question is it the same? Okay, you may think that this is completely stupid. You know, if you take a matrix, usually its operator norm is much, much bigger than the maximum norm of columns and maximum norms of rows. But it turns out that really in some cases in random matrices, this is the right upper bound. So for example, there is second result that, you know, you have to take IID things here, but not necessarily Gaussian. Any things IID you will take instead of this will be true. So if you have a matrix with IID entries, its operator norm, its expected value, it's more or less maximum of norm of rows, maximum of norm of columns. For IID entries, not necessarily Gaussian. For Gaussian, it was known, well, you know, from 70s.
So what is something is confusing because you say it's not IID, but then the GIJ are
Yeah, but AIJ are not equal.
They're still independent, but they're
Yeah,
not.
they are still independent.
So they are ID, but not IID.
Yeah. So the entries are multiples of IID, but not the same multiples.
So this is the important I is the independence.
Yeah. Obviously, without independence, you know, you may easily construct counterexample to this. Okay, so what is known that this is basically the case. It is much weaker. If you add the fourth moment assumption. So if you add the fourth moment, so for IID, usually this behaves like square root of n, this behaves like square root of n, and this behaves like square root of n, if you have fourth moment. So this is more or less the right estimate for IID, you know, if your entries are IID here. But if non-IID, then, you know, you may put here this AIJ, GIJ, so this thing and this thing is okay. But here you should have not fourth norm, but something like psi 2 norm or you know, something much weaker than, you know. Norm, you should have norm of coefficient, some Orlich norm with phi behaving like, I don't know, e to the 1 over x squared or some function like this. So much weaker here. Okay, so this is my favorite question because, you know, it shows that somehow the random matrices are, you know, very low dimensional things. Okay, so now let's go to my subject of the talk. So one estimate you may estimate Rademachers by Gaussian, and usually it works well. But there are some situations when you know that coordinates are well bounded, when this is wrong even in the case for p equal to 1. So for d equal to 1, so once recall this Hitchenko estimate, and you may, you know, dualize it, dualize this interpolation norm and write this in the form, okay, x2 smaller than square root of p. If there will be no this term, it will be just Gaussian. And then, you know, assumption on the boundedness is hidden into this x infinity. And actually there is, you know, there is a version of this Hitchenko with very nice constant. So it's almost Gaussian if you forget about p2 largest coefficient. I mean, here it's 1. So it's, you know, this is Gaussian. Okay, but it's side remark. Okay, so for order 2, things are a bit easier. Why? Why they are easier? Because if you do this you decouple, use induction, then what you have to estimate will be a form in one random variable. So something simple usually. And okay, I was able to show that this Hanson-Wright holds, you know, this is almost immediate extension. I mean, almost, you know, if we don't have this will be exactly Frobenius norm times square root of p. So this corresponds to the norm of a matrix treated as a linear form, and this treated as two linear form. Okay, so the things that Rademachers are bounded are hidden is in this introduction of this interpolation norm, or somehow, how do you call it, infinity parameter. Okay, so, and, okay, there was result of Warszawski and Adamczak for higher order houses in the spirit of Arcones and Ginet and Borel. Okay, it's exactly, you write the same result. This is general policy. You write the same result and you introduce some infinity norm. So not only L2 norm, but L infinity norm. And again, the problems are the same, but this is not so easy to estimate. Okay, so Okay, so again, something, you know, extremely hard probably to digest. Okay, without this, I would repeat a Gaussian norm. I have, you know, I treat a matrix as a multilinear form on L2. Here I treat them not on L2, but on some L2 with L infinity. So here should be infinity. Maybe I should, no, here should be 2, but L infinity is hidden in this maximum. So let's look what happens in D equal to 3. Okay, without this, it's exactly square root of variance. This is the same as Gaussian. Here you introduce this maximum of one variable. And because Rademachers are bounded, this is general. Okay, let's say. For splitting into two sets, you have again the same as for Gaussian, and you introduce this maximum. In 3 sets, you know, you may easily guess. So you may, you know, looking at this formula, everybody would guess what is for higher order. Yes, okay. So this is not very nice, but you know, this is a formula. It doesn't involve randomness. It's based on deterministic quantities. Also, probably not very easy to estimate. Yes. Okay. So what is the statement? The statement is that lower bound works for any D, and the reason for this is you know, I told you it's easy induction. The upper bound, so far we are able to show for D equal to 3, and you know, for Gaussian causes the situation was as follows, that for the difference between D equal to 2 and D equal to 3 was huge, and between D equal to 3 and D equal to 4 almost no difference. So if you understood the result for D equal to 3, you may get the result for D equal to 4 and at higher. Here it looks to us that still there is something. So you know, still the proof of this result is not so nice. So we decided to stop thinking at some moment and get this. Okay, so for D equal to 2, this agrees with these previous results. Obviously, the method is decoupling. So in fact, we prove not this result, but okay. So here I wrote decoupled. But you know, if you use the decoupling theorem of Montgomery-Smith at De La Peña, we will get similar estimate for undecoupled houses. So without these ones here under symmetry assumptions, and you know, you may reverse it using this. So you may get estimates on tails, but it's not so nice as the Gaussian case, because this function is not a polynomial, it's sub-polynomial, so it's not so easy to find an inverse here. But you know, it doesn't matter moments of tails. Okay, so I promised you to show why the lower bound is trivial, and here is the only trick we are using. So the trick is the following one. That, you know, if you have independent symmetric random variables, so if xi are independent symmetric, then this is the same as you put modulus here. Because of symmetry, yes, you may, you know, it doesn't matter if ai times xi, it has the same distribution as this for symmetry. However, for higher order matrices, this is one of the problems about houses, that this is not longer the case. You know, the life will be extremely simple if we have this. So if we would be able to put moduli here, because then we will be working with matrices with non-negative coefficients, that, you know, it's usually much easier to bound them. But you know, usually it's bigger, this thing. But for order 1, for sums, it's the case. So what do? You use induction, obviously. So you look this. Okay, you treat in special fashion 1, let's say first variables, and then, you know, using this trick, you put moduli inside of the sum. You put moduli and then to the p power. So here does this observation, and then Okay, you have expectation with several independent sinks. So you may put one of these expectation. This 2d minus 1, it means that you take expectation with second, etc. Okay, I should write d up to here. Okay, in this. And this is just expected value of not piece power, but of just L1. And we know that for houses, L1 norm and L2 norm are comparable with a constant polynomial indeed. So exponential indeed. So instead of L1 norm, we may write L2 norm. And now what's the gain? This is linear form. So we know by Hitchenko result what is this. This is exactly like this. And you may, if you look at this, it will turn out that this is exactly this 1 over d norm, like this thing, if you look carefully. Okay, so this bound is, as you see, this is the whole proof. For other quantities, you use induction and this observation. But supremum, expected value of supremum is bigger than supremum of expected values. Okay, so what are two main ideas about the upper proof? One idea is concentration. So either you may use Talagrand result on concentration on discrete cube because norm is convex and use his result, or use usual Gaussian concentration and instead of Rademacher's use this exponential, not exponential, but uniform distribution on -1, 1. So if you want to avoid Talagrand, a non-easy result, you may use here uniform, and then there will be this concentration also. Slightly easier to show. So the deviation from supremum from expected value is governed by exactly this. So this is this Hitchenko estimate. So this might be right here. This x1 p epsilon is just sum of xi star up to p plus square root of p sum of more or less like this. Okay, so this is this. Okay, so this is basically Talagrand. So this tells you that if you split the set into exponential number of sets, then the expected value over supremum of some of the set is smaller than maximum of supremum plus c times this norm. Okay, it's a standard fact used in many papers of Talagrand when he was proving majorizing measures. It's nothing deep. Okay, so now you should be able somehow to split the sets into exponential number of things. Okay, and what do I? Okay, I'm sorry. What was this? Okay, and you have this decomposition result. So if you have a subset of b to n by b to n, you may decompose it into basically exponential number of things, such that if you look at the operator norm of some, not necessarily Gaussian thing, so this is like operator norm, but you don't have coefficient from b to n by b to n, but from some smaller subset. Then it is much smaller than trivial bounds. So it is like this variance band, but divided by square root of p, without other terms. So other terms for Gaussian is a constant here. So this is. Okay. So maybe I will skip the next technical slide. I will only say that, okay, what is so special about Rademachers and Gaussian? So is this very special class? It turns out that not, that there is much larger class of random variables that it works for. The only thing that you need is that probability that x is bigger than t is e to the concave function, so e to the negative convex function. So for Gaussian, this function is basically t squared. For Rademacher, is infinity up to some point and 0 after. So it's nice convex function. And other things are exponential, and you may as well do these things for these random variables. So instead of Rademacher, take for example exponential. Okay, so here there is extension of this Hitchenko result or Montgomery-Smith to such sums, and you see this is like operator norm of this sequence on AI. Okay, and for example, for exponential, it's in the Hanson-Wright estimate exactly it was after some point t maximum di plus square root of p sum of square root of di squared. So this is exactly the same estimate because gi squared behaves like exponential. So it's not a pure coincidence. Okay, so for example, for d equal to 2, here is the result. Okay, so again, you have some not very nice, but some deterministic norms. One is treating the matrix as 2 linear, one is treating as here 2 linear, this linear form. Okay, so this is just okay, and you may generalize to order 3, and what turns out that for the exponential case it works for arbitrary order. So there are really problems for higher order houses due to the fact that tails of Rademachers, or in other words, these norms grows much slower than Gaussian. If you know that these norms grow faster than Gaussian, basically you may be proven for higher order than D. Okay, so let me finish with some open questions. So one question, okay, I don't know how much worth it is studying, but probably one should first find a simpler proof for D equal to 3, or find some nicer idea behind, or I don't know, shoot something. So find upper bounds for causes of order 4 and higher. So the conjecture was there, that this lower bound agrees with upper bound, but still there is something to be done. Another thing which is also of interest, I don't know, maybe it is somehow related to the previous talk about influences, is about symmetric random variables taking on 3 values. So Rademachers take on 2 values, 1 and -1 with the same probability. Here you, except of this value, you allow random variable to take value 0 and symmetric. So it's this. So you take causes in these random variables. Okay, there are some conjectures by Warszawski, and he was able to prove them. Okay, so again, lower estimates usually works, upper estimates. Okay, it's quite messy, but he had something, but dependent on alpha. All right, so it's still not the result that you would like to have, that the constant depends on alpha. Okay, and it's open even for order 2, which is much simpler. It should be much simpler. There is one other case I think worth of interest because of nice formula for sums. So there is the following very nice theorem of Krzysztof, Steven, and Paweł. Then if you, instead of logarithmically concave case, you have logarithmically convex case. So something growing much, something decaying much slower than exponential. So like e to the, for example, t to the alpha, but alpha smaller than 1. So this is the case. Then the piece moment of combination is either variance or piece norm of the things. Okay, so if these random variables have these joint supports treated as a functions on omega, then this will be the right bound. This will be the bound if if p is equal to 2. So it's very easy to show that from below this is bigger. But the amazing is that it works from above. And because this formula is simple, that maybe formula for causes of order 2 will also be simple. So maybe and also such random variables like Weibull sometimes appear. So obviously this for Rademachers has some combinatorial flavor, a combinatorial application. Here there is none. Okay, my time is over. Thank you for your attention.
So you had lots of constants depending on D all over the place in your results. So are you able to say what C of D finally comes out to be, saying your Gaussian moment bands, and what do you think it ought to be
Okay, depending for Gaussian, you know, I'm not very sure about the constant in the decoupling, but outside of decoupling, it's like d to the d, more or less. But you know, if you go from decoupled to undecoupled, you lose another constant. I don't know if this is exponential in d or probably, but you know, for decoupled, it's like this.
And do you think that's the correct dependence on D?
Oh, it's very hard to say. You know, I would expect exponential in D, but you know, it's. I think the first question would be, for example, what is the constant in the decoupled case? When you go from undecoupled to decoupled, you know, if you make this trick, is it exponential in D or no?
Well, maybe we could have the two speakers.
Just maybe a naive question, but it looks that you can do to extend some of the properties of n by n Gaussian matrix to three-dimensional n by n by n matrices. And the question is there some hope that some of the theory of random matrices tend to higher dimensional matrices, or some aspect of it?
You know, this again touches this algebraic question. Yes. So what are
The hope comes from analysis, not from algebra.
yeah. But what are eigenvalues for you know, for higher order for multi-index matrices? So obviously operator norm is okay. So you may ask about the results about operator norm. But also there are plenty of results in the random matrix theory about this empirical measure based on eigenvalues. And here, what are eigenvalues for free linear? Yeah, it's a very good question, but you know, I'm too weak at algebra, so.
So maybe we thank the speakers this morning again.